Hello, everyone, and welcome. My name is Jerry Beanie, and I'm the Global Business Development Manager for the FLIR R&D and Science segment. And it's my pleasure to present this webinar to you today. We appreciate everyone taking the time out of your busy schedules to meet with us for the next 35 to 40 minutes in order to learn how thermal imaging can be used to accelerate product development and electronics design and testing. Before I begin, I did want to mention just a couple of housekeeping items. First, we plan to keep everybody muted during the slide presentation to eliminate any background noises as people might be logging on or maybe hopefully not doing work in the background. So if you do have any questions as we go along in the presentation, please feel free to type them into the question and answer panel as we go along. So I plan to spend, depending on exactly how much time we have, for, 5 or 10 minutes at the end of the presentation, trying to answer as many of them as I possibly can. So before I begin today, I did want to spend just a couple of minutes talking about some really exciting changes here at FLIR. If you're not already aware, FLIR was officially purchased by Teledyne Technologies back on May 14th, so just a few short weeks ago. And we are now referred to as Teledyne FLIR. And for anyone who doesn't know Teledyne, Teledyne's a global company that provides a variety of products and support services to help sense, transmit, and analyze information. And you may not realize it, but Teledyne enables many of the products and services you use today on a daily basis. And by adding FLIR's strong portfolio of infrared sensor technologies to their company, Teledyne Technologies is really uniquely positioned to provide a full spectrum of imaging technologies and products spanning from X-ray through the infrared and all the way out to the radio waves. And by adding FLIR's already strong product portfolio, Teledyne can now provide a full spectrum of products from the component level to complete imaging systems. Teledyne FLIR now also has the capabilities to provide a complete range of unmanned systems and imaging payloads across all the domains, ranging from deep sea all the way to deep space. And personally, we are really excited for what the future holds for Teledyne FLIR and the new opportunities to provide complete solutions to our past, current, and future clients across a wide range of different markets and applications. So now with that little update out of the way, let's dive into really the meat of the webinar and kick things off with a little infrared theory. And we talked about infrared cameras, and we obviously have to talk a little bit about level set everybody on a little bit of infrared theory. So the graphic you see here at the bottom of the slide shows a section of the electromagnetic spectrum where you can see how infrared or thermal radiation relates to other forms of electromagnetic radiation. And as you can see, the infrared region sits just to the right or actually it's to the left. Oh no, it is to the right of the visible spectrum. Sorry, the screen swapped for me. So the wavelengths of the infrared radiation are longer than the visible wavelengths our eyes are actually tuned to see, but they're shorter than like microwaves and radio waves. But just like visible light, infrared radiation travels through space at the speed of light, and infrared energy can be focused, it can be reflected and refracted just like visible light can. You just need some special materials or optics to do those tasks. So what is infrared radiation that I just mentioned? Well, as many of you are already aware, when a medium, which can be a fluid, a gas, or a solid, heats up above absolute zero, which is like, minus 273 degrees Celsius or minus 460 degrees Fahrenheit, the molecules within that medium start to move. And as these molecules move around, they collide with each other, creating an energy release in the form of photons. And as the temperature of the medium increases, so does the molecular movement and collisions. Therefore, an increase in temperature produces an increase in the release of photons. The form of energy transfer that is caused by that release of photons is actually known as thermal radiation, or also called infrared radiation. So thermal or infrared radiation is what is sensed or really seen by an infrared camera, as well as like IR temperature guns or spot pyrometers. But now that you know real briefly what infrared radiation is and how it's created, let's discuss on really how infrared cameras are actually able to sense emitted infrared radiation or that thermal energy and report it to you as a temperature value. And for the sake of a quick example, let's look at the new Teledyne FLIR A70 fixed mount cameras, which is one of our small entry-level R&D camera systems that is useful in a wide range of different temperature measurement applications. This camera has an uncooled microbolometer type of infrared detector. And a microbolometer is a small thermal based sensor, meaning it produces a resistance change when it's heated. The focal plane array in the A70 camera contains 640 by 480 pixels, which equates to over 307,000 individual detector elements. And each of those elements is a single bolometer. And with the lens of the camera, we actually focus the infrared radiation coming from the thing that we're looking at or the target onto that array of detector elements. So as the radiation strikes each bolometer element, they heat up and the respective resistances change. Then we use a readout integrated circuit to measure that resistance change on each element and then convert that reading to a digital count. That then digitized data for each one of those pixel elements is then calibrated to temperature and then streamed out over gigabit Ethernet or Wi-Fi to a computer running our FLIR Research Studio thermal analysis software. And because the infrared image being produced is made up of individual temperature measurements for each detector element, we can use analysis tools to highlight specific elements and display their respective temperature values. We can also use area tools to display minimum, maximum, or even average temperatures within an area, or use a spot tool to display the temperature value of an individual element within that infrared image. In the Research Studio software that I mentioned actually provides a really robust array of analysis tools like time versus temperature plotting, so that you can really investigate more deeply how temperatures change over time and many, many more different analysis tools. So if you think about it, the Teledyne FLIR A70 camera is like having over 300,000 thermocouples mounted to your test article or the object that you want to test. So so how is having like so many temperature measurement points within a thermal image actually useful? Well, let me provide you with really a real world example of the benefits of using the infrared thermal imaging based on an experience that we had with one of the world's fastest growing printed circuit board manufacturers. This company, like most, routinely used like thermal simulation models to predict where the heat loads would be present in their board designs and layouts. So based on these models, they would modify their design and often add heat sinks or maybe fans to help dissipate that heat. Then they use thermocouples or some occasionally spot pyrometers to validate that the fans and the heat sinks were working effectively. However, when the product was actually released and started shipping out into the market, many of their clients began returning boards due to early failures caused by overheating. So what was the first thing you think the company thought to do? Well, their first step was, of course, add more heat sinks and fans. But doing so just added extra weight to the boards, actually drew more power from the boards, which resulted in lost efficiency. And the solution actually resulted in an increase in the overall cost of the boards to the customers. So the company continued to use thermocouples and the higher temperature guns during that kind of troubleshooting and repair phase of the design, but the engineers still couldn't find the source of the failures. So after some significant investments in time and resources, they eventually decided to pick up the phone, reach out to FLIR to discuss how thermal imaging could potentially help them better understand and characterize the thermal performance of their device. And this is actually what they saw that day. So based on the description of the board and things that were in the stated needs of the engineers during kind of a pre-visit phone call, the FLIR sales engineer decided to bring along a couple of different entry-level FLIR R&D camera systems to the meeting in order to kind of demonstrate their ability to both measure the temperature of the different board components while also providing a visual understanding of how the product would actually heat up. The first camera he used was a FLIR A400, which has a detector format of 320 by 240, and which equals out to a resolution of just over 76,000 measurement pixels. And since the engineers were only used to getting kind of single points of temperature data, when they saw the first image from the infrared cameras, their jaw dropped. They had put the thermocouples in all the wrong locations, which are indicated on this image by the green boxes. They were nowhere near the hot spots, which might have been the cause of the failure. And additionally, the locations where they added fans and the heat sinks were not as hot as predicted by the simulation models. Their design had extra heat sinks and fans where they weren't even necessary. And in less than 5 minutes, that customer learned more about their board design's heat signature than they had in months of using simulation models, thermocouples, and spot pyrometers. And the FLIR infrared imaging camera had an immediate payoff. But of course, being the savvy person he was, the sales colleague knew there may be even more to see on the board. So he connected up a FLIR A700 camera, which has 4 times the pixel resolution in a 640 by 480 detector format. Than what the initial A400 that he used, and he took some images of the board. And unknowingly, they actually uncovered a different, totally unique hotspot in a remote area of the board that no one had even considered. And only by using that high resolution infrared camera were they even able to find that hotspot that day. So this is really a great real world example of how infrared thermal imaging can provide a number of advantages over the standard temperature measurement devices a lot of people use in the design and testing of electronic systems. With infrared cameras, you get thousands of points of temperature measurement without even touching the surface. The results are immediate and they're intuitive. I mean, a picture's worth 1,000 words, and they provide a more complete thermal characterization of the device, both in the R&D stage, and it can also be done in the manufacturing stage in the whole product development cycle. This really helps to reduce the test times. It makes the interpretation and sharing of data with colleagues and maybe even customers really easy. So, and as the electronic systems and packages just continue to get smaller and smaller, the challenges of heat management is just increasing. I mean, imagine, going from that printed circuit board in that real world example that it was roughly, I think, like 9 inches by about 13 inches, and scaling that down to a device the size of, like a smartphone, or individual components, only 100, a few hundredths in micron in size. Our spot guns are really kind of incapable of measuring temperatures on components of that size. And the components may be actually even too small to even accommodate mounting a thermocouple to them. And of course, a solution could be to attach an RTD probe, which is similar to a thermocouple, but actually a bit smaller. But even this smaller probe might skew the temperature measurement data because it can act as a heat sink as well and wick temperature away from the device. So infrared cameras, offer a non-contact solution for characterizing the thermal properties of the entire device, but they can only be used to measure the temperature, but they can also be used to measure the temperature of individual components. To do this, you just need to make sure that the camera system has the appropriate spatial resolution to accurately measure the temperature on the devices you're interested in measuring. But what is spatial resolution? If you don't know, or anyone who's not really familiar, the spatial resolution of an infrared camera, which is often referred to as the IFOV or instantaneous field of view, is the minimum target size an infrared camera can image. It represents really what a single detector or pixel element will see at a given distance. And the spatial resolution of the infrared camera system can vary based on the dimensions of the camera's infrared detector, the pixel pitch, what lenses are being used, as well as the working distance between the camera and the object that you're testing. So if the size of the individual component you're interested in measuring is smaller than the spatial resolution of the camera system, the temperature of that component will be actually averaged over that single pixel. So even if the component is hotter than its surroundings, you may not even be able to see it. And you definitely won't be able to accurately measure its temperature. So to accurately measure the component, it actually must fall squarely on that one pixel or detector element. But this is, typically just impractical from a fixturing and testing scenario because things obviously move around. Surface mount components aren't exactly in the same location, every time after they're wave soldered. So to account for this, the typical rule of thumb is that you want to have at least 3 by 3 grid of pixels, or a total of 9 pixels on the smallest thing you want to measure in order to achieve an accurate temperature measurement. This 3 by 3 pixel area is also often referred to as the measurable spot size. So of course, having more measurement pixels covering the object you want to measure will often actually result in more accurate temperature readings. So we actually typically try to recommend infrared camera systems that can provide at least 100 measurement pixels, or like a 10 by 10 grid instead of a 3 by 3, and or more, than 100 for any of the features or components that you're interested in measuring. Um, but really, people ask, like, all right, how do you know what Teledyne FLIR camera system is really best for your application when it comes to space resolution? So fortunately, when you're considering a FLIR infrared camera for your application, we have a number of tools that can help you determine the overall field of view as well as the space resolution for a specific camera and lens combination. The FLIR Technical Support Center website, which is flir.custhelp.com, actually has the online field of view calculators for nearly every camera we sell. As you see on that image on the left-hand side, you can simply select one of the available lenses from the pull down, enter the expected working distance, and click the calculate button. And the online tool will then output a table of all the expected horizontal and vertical fields of view, along with the spatial resolutions at that given distance in both English as well as metric units. It will even provide the depth of field details as well, which is actually really nice, especially when you start getting to more close-up, close-up lenses and things of that nature, or printed circuit boards that have a lot of, like, tall features on them. So, and if you happen to actually input a working distance that's outside of the limits of a particular lens, the field of view calculator will provide an output value. Won't actually provide an output value. So it's actually a really good sanity check. So if you would like, more details on kind of the math behind the field of view calculator, or like more fidelity in the inputs and outputs, we also have Excel-based, field of view calculators that can be provided upon request. Like the online tool, that spreadsheet allows you to input the focal length of the desired lens, for a given camera, as well as the expected working distance. And the spreadsheet will then go ahead and calculate that, again, that horizontal and vertical field of view in meters, feet, and inches, as well as a single pixel spot size or space resolution in millimeters, inches, and feet. So the spreadsheet, however, the one downside is it doesn't have any type of mechanism to alert you when you specify a working distance that is outside the capabilities of a selected lens. So there's a little bit of a watch out there. But the nice additional feature of the spreadsheet is it also shows you um, or allows you kind of to enter the horizontal and vertical dimensions of the article you're going to test, or the unit under test, or UUT in the spreadsheet. And it will actually calculate or determine how many pixels will actually be on that object you want to test in both the horizontal and vertical directions based on the calculated spot size for the system. This also provides an output of the percentage of the detector that's actually being used to image the unit that you're testing, which really kind of helps ensure that you're really working to maximize the number of measurement pixels on the target, or your object that you're testing, given your selected camera lens combination as well as your working distance. So, okay, but how do you know which of the FLIR Teledyne thermal cameras is the right one for your electronics design and testing applications beyond just, the determining spatial resolutions and field of views? Well, If you're new to thermal imaging, or have a limited budget or expect, target sizes that are relatively large, one of the new, A-series R&D kits really might be an ideal solution for you. Um, the new A50 and A70 research and development kits are really great low-cost solutions for engineers and technicians who need a thermal imaging camera for like the applications like quality assurance or troubleshooting of printed circuit boards. They're also perfect systems for university research programs and life science studies where you need to, where there's a need for more flexible systems that provide kind of quality thermal data, and that's super important. And with unique features and ease of use of these kits, they can be deployed in really multiple situations within commercial research and development, where accurate non-contact temperature measurements are really needed to support, any critical design decisions that you may have. And since the A50 and A70 cameras are built on the same platform, they share all the same basic features, whether it's the simple gigabit Ethernet connections, that's also PoE or power over Ethernet, that allows that digital data stream, into the FLIR Research Studio software that's included in the kit, or or the camera's really kind of small form factor and straightforward mounting. The cameras are simple to install and really easy to use. So, and when you add in the plus or minus 2% accuracy and the expanded calibration range up to 1,000 degrees Celsius, the A50 and A70 cameras are really a great entry-level thermal camera platform for R&D and science applications. So these new A50 and A70 research and development kits are offered in actually 2 different detector resolutions, and 3 different lens options. The A50, it has a 464 by 348, which is kind of a weird resolution. And then you can select either a 29-degree, a wider angle 51-degree, or even an ultra wide angle 95-degree lens. And this is the same for the A70 camera, that actually has a 640 by 480 resolution. This selection of camera resolutions and lenses really offers significantly more flexibility than some of the single lens choices we offered in some of our previous thermal benchtop test kit systems. And the options for the ultra wide field of view with a 95-degree lens really increases these new cameras' abilities to be used in a really wide variety of different applications. And just like if you're familiar, been on one of the previous webinars with me, it's just like the A400 and A700 science kits we launched last year. The A50 and the A70 cameras utilize a standard gigabit Ethernet connection for that digital data streaming into the FLIR Research Studio software. So in the research, and the research and development kits, come with a 1-year license of that Research Studio software, which really gives you the ability to work in the operating system environment and language that you're most comfortable with. It supports both Windows, Mac, as well as Linux, as well as 22 different languages. It also gives you the ability to connect, record, and analyze thermal data quickly than ever before, thanks to a really easy to use interface with it, with a really simple workflow that allows you to kind of get up to speed with not a lot of training. So if you're not familiar with our new Research Studio software, that new platform does provide a number of unique features that allow you to quickly acquire the thermal data you need to support decisions, without really that need, as I mentioned, for extensive training. And the ability to connect, view, and compare data from multiple thermal cameras. You can connect multiple thermal cameras to the software all at the same time. You can open up multiple recorded files simultaneously. Means that you can analyze and compare critical temperature information in some really unique ways. And while the ability to save and recall and share workspaces that you set up within the Research Studio environment, means that you don't have to waste a lot of time reconfiguring the user interface each time you're going to run a test. So, but a lot of people ask, but is A50 or A70 R&D kit the right system for my needs? Well, the best thing to do is talk to a FLIR salesperson or maybe schedule an on-site demo. But for the sake of the webinar, we can actually run through kind of a really quick test as a way to demonstrate the capabilities. So we'll use for simplicity, we'll just use the Teledyne FLIR A70 R&D kit that comes with the standard 29-degree lens as kind of the basis for this discussion, as well as a powered Raspberry Pi as an example printed circuit board. That's something a lot of people are very familiar with, and using that as an imaging target. The Raspberry Pi, again, is a great test target because it's relatively small. I think it's like 86 by 56 or 58 millimeters in size, and has a number of like small like 0402 surface mount components on it. And the A70 R&D kit is a very affordable camera system that has a 640 by 480 format microbolometer detector with a total resolution of, again, like it's over 300,000 measurement pixels, but it's like really 307,200 measurement pixels. But the A70 does use manual focus lenses that you unfortunately can't be changed. So there's no close-up lens options available for these entry-level cameras. So if you're not familiar, with the various sizes of different surface mount components, I just wanted to show a quick screenshot that we took from Wikipedia that provides a pretty good rundown. The size range of like 0805 to 0402 are really kind of commonly used in electronics today, though they're getting smaller and smaller, as I mentioned. And actually, they're just all going to get even smaller as packages, electronics packages are required to get smaller and smaller as well. So, but for this experiment, we're going to focus on the 0402 components on the Raspberry Pi, as that's kind of as the assumed target of interest. And as you can see, an 0402 is only like 1 millimeter by like a ½ millimeter in size. So it's actually really small. So the A70 camera with that 29-degree lens has a minimum focus distance of 250 millimeters. And at that distance, the A70 camera, provides an overall field of view of 134 millimeter by 101 millimeter, which is larger than actually the entire size of the Raspberry Pi. But if you divide that 134 millimeter by 640 pixels and the 101 millimeter height by 480 pixels, you'll note that the instantaneous field of view or spatial resolution of the camera system at that working distance is 0.21 millimeters or 210 micron per pixel. So now think about it, like how many of these 210 micron by 210 micron pixels fit on that small 0402 component that's only 1 millimeter by ½ millimeter in size? Well, if you do the quick math in your head, it's roughly 10, with just 5 pixels across the long axis of the 0402 and just 2 pixels along the short axis. So this will allow you to see thermal differences between the components and the board, but could result in suboptimal data if you're trying to measure the actual temperature on the 0402, because you don't have quite enough number of pixels. So in order to achieve smaller space resolutions, you would need to use a different camera, since the A70 doesn't allow for the use of additional close-up lenses, but it's really good at gross thermal analysis and determining where maybe some hot spots or hot components are located. You're just not going to be able to drive down to determining exactly the thermal characteristics across the device. So for just a bit more, cost, you can get an A400 science kit that comes with FLIR macro mode and the Research Studio software. And although the A400 camera has an overall resolution of 320 by 240, which is actually less than the A70, the macro mode feature makes it a very flexible system. So with macro mode enabled, the working distance of the A400 to the Raspberry Pi drops to just 60 millimeters. So, and the overall field of view shrinks down to like 32 by 24. And you can see that we can clearly make out those surface mount components. And again, if you divide the overall field of view in both the horizontal and vertical directions by the camera resolution, you'll see that the spatial resolution for this setup is 0.101 millimeter or 101 micron per pixel. And like like before, do the math real quick kind of in the head, the number of pixels, how many of those 101 micron, by 101 micron pixels actually fit on the 0402 surface mount component. Well, again, it's roughly 50, which is like 5 times more than the A70 R&D kit with the 29-degree lens. So this means you're getting really good temperature measurement data on the 0402. But you know what? We could actually do better. So what happens if we put an available 2x close-up lens on the A400? With this lens, the working distance of the A400 is just 18 millimeters, which, I mean, it's less than an inch, like 3/4 of an inch. So it's close, but it still allows room for probes and other instruments to be used during the testing. So, and with this lens, the overall field of view shrinks to just 15 by 11 millimeter, and you can see the individual components more clearly. So by performing that same math, you can determine that that IFOV, or space resolution, is 49 micron per pixel. This means for the A400 and 2x lens, setup and camera system, you'll end up with a total of 200 measurement pixels on that single small 1 millimeter by 0.5 millimeter size 0402 component. So if you want to make temperature measurements of this size, you'll be getting really great data. But the best part too is you actually are going to be able to see the thermal variations across that actual component. So as you can imagine, there's a wide variety of applications where Teledyne FLIR infrared cameras can provide meaningful thermal data and critical decision support. With the ability to measure temperature on a wide range of target sizes, they're ideal for electronics design and testing applications like general circuit board design, failure analysis, and quality assurance. Our infrared cameras can also help support green energy development in the current efforts to optimize energy handling to reduce energy waste and increase efficiency. And the advanced features and kind of compact design of the cameras, in addition to the analysis capabilities of the FLIR Research Studio software, really gives test engineers and technicians a flexible temperature measurement tool to support critical testing and validation needs. Thermal imaging can also help diagnose thermal runaway in power electronics and batteries. And for those of you who aren't familiar with the concept, thermal runaway is basically a situation where the current flow through a device causes the device temperature to rise. But actually that rise in temperature causes an increase of current flow, which in turn again causes an increase in rise in temperature. And this can happen in both semiconductor devices as well as batteries. And as you can imagine, it's kind of a critical component to understand and try to eliminate because this kind of uncontrolled escalation of temperature can really actually have, result in kind of some cataclysmic events, especially when you get into really large batteries. So in summary, with infrared imaging, really kind of like where the rubber meets the road is in the testing and identification of problems that once may have been impossible to find or at least really difficult to locate quickly. For manufacturers, the return on investment are the images that really kind of pinpoint a design flaw that and help like reduce testing times and really that time to market, which will save the project costs in the long run. So thermal imaging also allows engineers to see kind of that complete thermal map of the circuit board with temperature values for each individual pixel in that image. There's no concern about mounting thermocouples or RTDs in the wrong place based on some wrong assumptions or some wrong models that could potentially, as you saw, result in some erroneous readings. And thermal images show exactly where the hottest points are on the board, as you saw in that real world example. And of course, thermal imaging can be employed at multiple stages of the design cycle and research and development process, beyond just simple like, circuit board imaging. Thank you, everyone, and have a great day.